Hello everyone, welcome to the second part of tutorial 4. So we begin with question number 6. In question number 6, you are asked to either prove or disprove the following. You are given a function f from the set A to itself, and you are given that the function is a surjective. Then the question is it necessary that the function is a bijective as well? It turns out that the statement is true provided your set A is a finite set. Okay, because indeed if the set is a finite set and the function is from the same set to itself and surjective, then we can show it is a bijective function as well. So we will touch upon this fact sometime later in this course, but the statement need not be true if the set A is an infinite set. Okay, so here is a counter example. So imagine the function f given from the set of set 0 to infinity to the set 0 to infinity. So that is my set A, and the function is defined as follows. The mapping of 0 is 0 and the mapping of 1 is also 0. Okay, so clearly the function is not injective, not one to one. And what about the mapping of the remaining elements? The mapping of element 2 is 1, the mapping of element x is x minus 1, and so on. So it's easy to verify that the function is indeed a surjective function because you pick any element y from the set 0 to infinity. The pre-image for that element y will be y plus 1 because f of y plus 1 will be y as per the function f we have defined here. So clearly my function is a surjective function, but it is not one to one, and that's why it's not a bijective function. The problem due to which we can't say it is a bijection is because the set over which the function is defined can be an infinite set. Okay. In question number 7, you are given an equivalence relation over a set A, where the set A has 30 elements. And since it's an equivalence relation, the relation partitions the set A into 3 subsets, each of equal size. Okay, so the question asks you how many ordered pairs are there in that equivalence relation. So since the subsets A1, A2, A3 constitute a partition of the set A, and it's also given that the size of each subset is same, and since the number of elements in the set A is 30, we get that the size of each subset in the partition is 10. Now recall when we showed that for every equivalence relation there is a partition, and for every partition there is an equivalence relation. We showed that if you are given a partition, how you got the corresponding equivalence relation whose equivalence class will be giving you that partition, right? So in that construction, our equivalence relation was consisting of all ordered pairs of the form I comma j, where for every subset ak in your given partition, if the elements I comma j are present in that subset, you add the ordered pair I comma j. Okay, so based upon this fact, we get here that the elements of the subset A1 within the partition will contribute to 10 square ordered pairs of the form I comma j, and they will be added to the relation R. Similarly, you have 10 elements within the subset A2, and they will contribute to 10 square ordered pairs as per our construction in the relation R. And in the same way, you have 10 elements in the subset A3, and they will contribute to 10 square number of ij ordered pairs or ordered tuples in the relation R. So as a result, the number of ordered pairs in our equivalence relation will be 300. In question 8, part ABC, we are supposed to count certain things. So you are given two sets x and y consisting of m and n number of elements. So I am calling the elements of x set as x1 to xm and the elements of the y set as y1 to yn. We are supposed to find out the number of functions from the set x to y. Okay. It turns out that the number of functions will be n power m. Why so? because when we want to build a function from the set x to y, each element xi from the set x has to be assigned an image. That's the definition of a function. Now, how many ways I can assign an image for the element xi? Well, I can assign y1 as the possible image for xi. I can pick y2 as the possible image for xi, and in the same way I can pick yn as a possible image for the element xi. So there are n possibilities when it comes to assigning image for an element xi, and the image for xi and the image for xj, they are independently picked, or images are independently picked, right? There is no dependency between the images of xi and the images of xj. Okay, that's important here because we are just interested in counting functions, the number of functions. Okay, that means it might be possible that the image of xi is same as the image of xj, right, and so on. So there is absolutely no restriction on the way we can pick the images for xi and we can pick the images for xj, right? So based on all these observations, we can say that I have n number of possibilities when it comes to assigning image for x1, and like that for each of the elements from the x set I have n possible images which I can choose, and that's why the number of functions are nothing but the number of ways I can pick the images for each of the element from the x set. That's n into n into n m times, which is nothing but n power. Okay. Part B asks you to find out the number of injective functions from the x set to y set. Well, we will be using more or less similar argument that we used for part A, except that now we can't say that the images for every element xi is chosen independently. Okay, because now we are counting, or we are interested in the injective functions, and in injective functions for every distinct element xi from the set x, you have to assign a unique image. You can't have both x1 and x2 getting mapped to the same element in the y set. So that's why when it comes to selecting image for x1, I have n possibilities, but once I have decided the image for the element x1, I can't assign that image to be a possible image for the element x2. That's why for x2 I have n minus 1 possible images, and like that when it comes to once I have fixed the images for x1, x2 and x of m minus 1, when I am assigning the image for the mth element from the x set, that image has to be different from all the images which I have selected for the previous elements of the x sets. That means I have only these many number of possible images, namely n minus m minus 1 possible images to assign for the element xn. So that's why the total number of injective functions will be now n into n minus 1 into n minus 2 into n minus 3 into n minus m minus 1. Okay. Part C asks you to find out the number of bijective functions from x to y. So the first thing to observe here is that for a bijection from x to y, we need the cardinality of the x set and the y set to be the same, right? It is very easy to verify that if their cardinalities are different, then we can't have a one-to-one and onto mapping between the x from the x set to the y set. Now, if the cardinality of the x and the y set are same, that means I am talking about the case where m is equal to n, then any bijection from the x set to y set can be considered as a permutation of the elements x1 to xn, right? Because I can imagine that I have n number of elements here and I have also n number of elements here, and each xi has to be assigned a unique image. Okay, so that can be interpreted. So if x1 is assigned as the image yi, right, as per your bijection, then I can imagine that x1 is getting shifted to the ith position. That way I can think a bijection between the x set to the y set. Even though the mapping of x1 is yi, I can interpret in my mind yi to be same as xi, and as a result, if I do this logical mapping, I can interpret a bijection from the x set to the y set as nothing but a permutation of x1 to xn. And how many permutations I can have for n elements? I can have n factorial number of permutations. So that will be the number of bijective functions from the set x to the set y. Okay. In part D of question 8, we are introducing a function, the S function. This function is also called as Stirling function of type 2. Okay. And this is a very important function when it comes to combinatorics. We will encounter it later again. So what exactly is this function? This is a two-input function. It takes an input r and an input small s, and it denotes basically the number of ways of partitioning an r element set into s non-empty disjoint subsets. Of course, s has to be less than or equal to r. So you have a bigger set, okay, call it any a, whose cardinality is r, and basically we want to find out how many ways I can split this bigger set into a pairwise disjoint subsets, basically s number of pairwise disjoint subsets, okay, such that their union gives back you the original set. So there might be several ways of dividing this bigger set A into s number of pairwise non-empty disjoint subsets. The number of divisions is nothing but the value of this Stirling function of type 2. Now, using this Stirling function, we have to count the number of surjective functions possible from the set x to the set y. Okay, so since we are interested to find out the number of surjective function, remember, in a surjective function, each element from the codomain set should have at least one preimage. Well, it can have more than one preimage as well. So let me define the set Ci to be the preimage set of any element yi from the codomain set. Namely, whichever elements could be the possible preimages for the element yi, the collection of those preimages, I am calling it to be the Ci set. Now it is easy to see that if I take any surjective function, with respect to that surjective function, if I focus on this preimage set of element y1, the preimage set of the element y2, and like that the preimage set of the element yn, then each of the collection of those subsets, the collection of those preimage sets will constitute a partition of your set X, namely the domain set. Why so? So it is easy to see, first of all, that the intersection of these preimage subsets will be empty set. You can't have an X present in both C1 and say Ci. That means you have two possible images for the element X, which is a violation of the definition of any function, right? And it's also easy to see that if I take the union of these preimage sets, I will get back the domain X. Why? Because as per the definition of a function, each element x, little x from the set capital X will have an image. So that's the way I can interpret any surjective function. You give me any surjective function, and if I focus on the collection of preimage sets of various elements from the codomain, that will constitute a partition of the domain set. Okay. So now what we will do is we will and how many such partitions can we have for the set X into n non-empty disjoint subsets? I can have S of m comma n number of such partitions. So now we are interested to find out how many surjective functions we can have. So what we can say is, if you want to construct a surjection, you first divide your set X into n pairwise non-empty disjoint subsets. Okay, call them as C1 to Cn. How many such partitions you can have? S of n, m comma n number of such partitions. Now, once you have divided your set X into n pairwise non-empty disjoint subsets, okay, each permutation of those subsets leads to a surjection. So what I am trying to say is, you have divided your set X into subset x1, x2 and xn. Okay, well, here I am calling them as basically C1, C2 and Cn. And now C1 could be the pre-image set of either y1, or it could be assigned as the pre-image set as y2, or it could be assigned as a pre-image set of yn. Now once we have decided that C1 is going to be the pre-image set of which element from the codomain, we next have to assign the subset C2 to be the possible pre-image set of any element from the Y set except for the element which has been assigned to this subset C1. And like that I can continue for the remaining subsets in my partition. So that's why I am saying here, once you have decided the subsets within your partition, you take any permutation of that corresponds to a surjection. So that's why the total number of surjective function will be S of m comma n times factorial. Okay. In question 9, we are continuing with the notion of our Stirling numbers, and you are supposed to prove that the Stirling function satisfies this recurrence condition. So to prove this statement, consider a set X which has m plus 1 number of elements. Okay. And we want to divide this set X into n pairwise non-empty disjoint subsets. We want to find out how many ways we can do the division. So my claim is, whatever way you divide this set X into n number of pairwise non-empty disjoint subsets, the division can be of one of the following two categories. Category 1 division, where the first m elements in the set X are divided into n minus 1 number of pairwise non-empty disjoint subsets, and the last element x of m plus 1 is occupying a solitary position in a single subset. Okay, so like that you have now total n number of subsets. n minus 1 number of subsets, their union will give you x1 to xn, and you have an additional subset which has only element x of m plus 1. That's one category of partition of the set X. How many partitions in this category we can have? The number of partitions in this category is nothing but S of m comma n minus 1, because basically the number of ways in which you can partition the first m elements into n minus 1 number of pairwise disjoint subsets, in each such partition you just add one additional subset consisting of the solitary element x of m plus 1. That will give you a valid partition for the bigger set X. And the number of such partitions we can have here is nothing but S of m comma n minus 1. That's one category of partition. The second category of partition that we can have for the set X will be as follows. I divide the first m elements into now n pairwise non-empty disjoint subsets. I can have S of m comma n number of such subsets. Now what about the element x of m plus 1? Well, we can either include it in the first subset or in the second subset or in the third subset or in the last subset. And that will give you an overall valid partition for the bigger set X. And clearly the partitions in this category are disjoint from the partitions in the first category, because in the first category of partition, the element x of m plus 1 is present alone in a single subset, whereas in the second category of partition, the element x of m plus 1 is not the only element within its subset. It's present along with some other elements as well, right? And you can't have any other third category of partition for the subset X. You can have either partition of type 1 or partition of type 2. Now, how many partitions of type 2 I can have? I can have n into S of m comma n number of partitions. This is because the element x of m plus 1 can occupy any of the n subsets. Okay, and plus because the two categories of partitions are disjoint, and if I sum them, I will get all possible ways of partitioning the set X. In question 10a, you are asked to either prove or disprove that every non-empty symmetric and transitive relation is also reflexive. Well, we can give a very simple counter example to prove that a statement is false. Imagine you are given a relation R over this set X. The relation is clearly symmetric. It's also transitive. Okay. If you are wondering why it is transitive, you have 1 comma 1 and 1 comma 1 present, and also 1 comma 1 present, and you have 1 comma 2, 2 comma 1 present, so you should have 1 comma 1 in the relation, which is present in the relation. But the relation is not reflexive because 2 comma 2 not present. In part 2, you are given two functions f and g from the set a to b and b to c respectively, and you are also given that the composition of g and f is injective. And the question is it necessary that f is also injective? The statement is true and we can prove it by contradiction. So imagine that GOF is injective but f is not injective. Since f is not injective, that means I have a pair of distinct elements from the A set, say A1 and A2, getting mapped to the same image, say B, and say the image of B as per the G function is C. Then I get a contradiction that GOF of A1 and GOF of A2 are same, namely C, but A1 and A2 are different, showing that GOF is not injective, which is a contradiction to my premise here. Okay. In question 10c, you are given that GOF is injective. Then the question is it necessary that G is also injective? Well, we can give us counterexample to disprove this statement. So take this f function and g function. Clearly, GOF of A1 is C1 and GOF of A2 is C2. Okay. So clearly my premise is satisfied here. GOF function is injective. But what about the G function? It is not injective. You have G of B3 and G of B4 both mapping to C3. So G function is not injective. So this statement is not necessarily true. Part D, you are given the f and g functions and your GOF function is surjective. None. Is it necessary that the function f is also surjective? Again, this is not necessary. Here is a very simple counter example. This is your f function, this is your g function. Your GOF is surjective because indeed there is only one element in your set C, namely C1, and the pre-image for that C1 is A1 because you have GOF of A1 being C1. So the function is indeed, GOF is indeed surjective, but the function f is not surjective because if you take the element B2, it has no pre-image. Okay, so that shows this statement is not necessarily true. So that brings me to the end of part 2 of tutorial 4. Thank you.